Fab can start.
Great. Thank you, everybody. My name is Fabrizio Sabba, and I'm the chair of the Student Postdoc Service Committee with the ASP. And today is the first seminar or faculty seminar series. And I would like to give the floor to Manish to introduce the speakers.
All right, so thank you for attending this seminar. It's been a successful series for our community, and we encourage uh, people that are on the faculty market to try out this process of faculty hiring through this and some interviews. So our first speaker today is Yanghua Duan. He is currently at Yale University as a postdoc with Manny Al-Malik. He did his undergrad at Tongji University and then a master's and Ph.D. with David Sedlak at UC-Berkeley. So the floor is yours, Yanghua. Go ahead.
Mm. Okay, good morning and good afternoon, everyone. So first, I want to thank you very much for coming here, and I would like to also thank you for the AESP HR committee to have this happening. So now I want to introduce about my research on how I developed selective physical chemical processes to enhance environmental sustainability. So as we now all aware of, that our current environment is not sustainable and this also is not resilient. So we often witness we have severe cold and also very intense hot simultaneously happen on different places. And while some of our cities get flooded very badly, we also see other places suffer from severe drought. In order to address this environmental challenge, I believe there are three main sectors that we need to conquer as environmental engineers. And those three sectors are water, energy, and the environment, and climate to address the overall environment. So I believe in order to do that, we need a revolution for our environmental system to improve the sustainability and resilience. But before we talk about the revolution and talk about the changes, I want to give you a quick overview of how the current system works. Our current environmental systems relies on the centralized systems. Those systems are linear, and they often rely on a single water and energy source. So let's use drinking water as an example. For drinking water treatment, we often take the water from a river or a lake. We send it to a drinking water treatment plant. We treat the water, and then we send it to the users. After we use it, we just dump them as waste. This approach makes the overall system very vulnerable to disruptions. They are also very inefficient to be used at remote areas because that requires high cost and long distance infrastructures. Eventually, those systems are energy and cost intensive. So when I'm envisioning the next generation of environmental systems, I often envision a system that is distributed system. Those systems are circular and they can often rely to use diverse water and energy sources. For example, we can easily integrate renewable energies into these treatment systems. And also we can harvest what we traditionally think as a waste as a potential resources. For example, rainwater, industrial wastewater, or contaminated shallow groundwater can all be used to augment our drinking water supply. And because of this diverse water and energy source, we can make this system very flexible and scalable. Because we avoid the long distance, high cost infrastructures, these systems better empowers the local community. Finally, these systems will be energy and cost efficient. So here is the vision we think about the systems. So what is the ideal technologies that we can actually build those systems? The Department of Energy's Desalination Hub, actually NAVI, National Alliance for Water Innovation, actually identified 6 criteria for those technologies called A-Prime: autonomous, precise, resilient, intensified, modular, and electrified. With those criteria, we can use to search for the ideal technologies. And based on my interest and my expertise, here I find 2 technologies that I think are very promising and I'm very interested in working with them. The first one is electrochemical treatment process. By using electrochemistry, we can generate chemical reagents at the locations where the supply of chemical reagents is often difficult. And by using electrochemistry, we can also remove contaminants by the redox reactions. And finally, by using electrochemistry, we can reduce carbon dioxide. We can capture and utilize the carbon dioxide to mitigate the climate change. And the other technology is membrane separation. By using a polymeric membrane, we can separate the unwanted species, such as contaminants or salts, from what we want, for example, water. And these two technologies both are very modular, they are scalable, and they can be used for a variety of applications at different scales. Those make this very promising to develop the distributed treatment systems. However, what are the technical issues or the research questions that often hinder the applications? In my opinion, the presence of interfering species for environmental samples is the biggest challenge. The presence of natural organic matter or chloride in water, for example, often hinders this process. They will compete for reactive species. In an advanced oxidation process, we often generate reactive species to oxidize the contaminants. But because the natural organic matter often exists at concentrations thousands of times higher than the contaminants, they will significantly hinder the removal of contaminants by the competition reactions. In addition to that, the presence of the interfering species, such as chloride, can also go through oxidative transformations to form toxic byproducts. For example, here I'm showing chlorate. So even when we are successfully removing contaminants by oxidative transformation, we may not provide a safe drinking water because we are also producing a secondary contaminants. Finally, the presence of this interfering species can often cause fouling or scaling on electrodes or membranes, which can completely stop the treatment process. And because of those reasons, we need a more selective process to selectively target the target contaminants and avoid the interfering of this interfering species. So now, first, I want to give you an example of how I used electrochemistry to develop the selective process for the treatment of non-traditional waters. I would not go through this figure in details, but because I will talk about each component individually later, but I want to focus on 3 different scales that how I address the selectivity challenge. I want to start with molecular scale, which I optimize the electrochemical reactions to enhance the selectivity in a molecular scale. Then from the treatment process scale, I want to focus on how I enhance the contaminant transformation selectivity from process optimization. And finally, by combining and optimizing these 2 electrochemical systems, I want to highlight the importance of using system optimization to enhance the overall performance in terms of hydrogen peroxide production and hydrogen peroxide utilization. So now, first, let's start with the first electrochemical components, the air diffusion electrode, which is made of carbon material or carbon paper. By using this air diffusion electrode, we can selectively reduce oxygen from atmospheric air into hydrogen peroxide. Because we have air all over the place, that means as long as we have electricity, we can provide the supply of hydrogen peroxide, a very necessary chemical reagents for drinking water treatment, and everywhere we want. So here's the result. We tested the performance for hydrogen peroxide generation under different electrolyte compositions. We tried in pure electrolyte. We also tried in storm water. And we also test under different operating conditions by applying different current density. As you can see, under different water compositions and different current density, we all show a very similar and consistent performance. That shows how robust our system is. And to give you a sense of what the concentration means, we actually generate about 700 millimolar of concentration of hydrogen peroxide, which is way higher, about 1,000 times higher than what we need for environmental applications. So this device is compact, it is intensified, and can be used for a variety of applications. because one of my focus is selectivity. So here I'm showing you how is the electron utilization efficiency or the selectivity, or we often call the Faraday efficiency for this process. A 100% Faraday efficiency means all electrons are selectively being used for the reactions we want. That is the hydrogen peroxide generation. And because of the very high Faraday efficiency, the overall cost for this process is very low. For example, to generate 1 kilogram of hydrogen peroxide, we only use 10 kilowatt hour of electricity. And if we calculate the price, the dollars per kilogram of hydrogen peroxide to generate on-site, it will cost only about $2. To give you a sense what that means, the conventional approach or the conventional supply of hydrogen peroxide at a remote location often costs about $150. So by using this device, we can provide chemical reagents at remote locations, and we cut down the price by a factor of about 100. Okay, now we have a good way to provide hydrogen peroxide at everywhere I want. The next question is how we use the hydrogen peroxide. Because hydrogen peroxide itself is a weak oxidant. It does not react with contaminants directly, and it requires activation. And one common approach to activate the hydrogen peroxide is to form hydroxyl radicals. As you can see, hydroxyl radical has one unpaired electrons, which make it very energetic, which makes it very unstable and energetic. They will want to react with contaminants to oxidize them. But the conventional approach, for example, using iron oxide, is very non-selective towards this process. When we add in hydrogen peroxide into the catalytic process, only produce less than 2% of hydroxyl radical. And most of the hydrogen peroxide actually goes through a self-decomposition reaction and go back to oxygen. So we spend so much energy and effort to producing hydrogen peroxide. We want to use them more selectively and more efficiently. That leads to my second development of the electrode, a stainless steel electrode. By optimizing the electrochemistry on stainless steel, I actually achieved the 1 electron reduction process for hydrogen peroxide. Through the 1 electron reduction process, I reduce the hydrogen peroxide to hydroxyl radicals. And here, the figure shows the selectivity of this process. As you can see, when we test the pH from 4 to 9, we first see an increase in the selectivity from 4 to 7, and then we see a drop. And the most important takeaway is what's the fraction of hydrogen peroxide is being used. So the selectivity we achieved is nearly 80%. However, as I mentioned earlier, the conventional catalyst usually is below 2%. So we increase this by a factor of maybe 40 to 100 for the selectivity. And also another one important takeaway I want to bring to you is the trend. Actually, you see the best performance is observed at neutral pH, which makes this technology very environmental relevant. And the previous reported catalysts often observed decreased performance at neutral pH. So this makes a very promising technology. So here, I hope I addressed the 2 methods I developed to increase the selectivity for the reactions we want at a molecular scale. So now let's look at the treatment process from a process scale. As I mentioned earlier, we will reduce the hydrogen peroxide to form hydroxyl radicals. The hydroxyl radical will react with contaminants. But that's not all. Because of the presence of nitric matters, nitric matter can significantly compete for hydroxyl radicals and often hinders our process. So we test this in the lab, and surprisingly, we actually see compare the result with versus without the presence of a nitric matter. We do not see a significant slowdown of the process. And when we actually go to measure the nitric matter by the chemical oxygen demand, we do not see any change on the chemical oxygen demand. That actually means we selectively oxidize the contaminants without oxidizing the nitric matter. It's very interesting. And the next question is like, why is that? In order to understand why we have this selectivity, I performed more additional tests by using probe compound with different charge. The first one is negatively charged benzoate. As you can see, based on the kinetic data, we would predict the removal follow the dashed line. However, we do not see any removal of the charged benzoate, and also we do not see any formation of its oxidation product. So when the probe is negatively charged, it's not going to be oxidized by this advanced oxidation process. In contrast, when we test the neutral compound, the 2-propanols, as we can see, we oxidize the hydrogen we activate the hydrogen peroxide, and then we form a lot of oxidation product from 2-propanol. That means the charge of the compound matters. And remember, natural organic matter is negatively charged. So for negatively charged compounds, the electrostatic repulsion between the negatively charged electrode and the compound will repel away from the electrode. Therefore, only the neutral contaminants is around the electrode. And this spatial separation provides the selectivity at a process scale. And finally, I want to talk about how a system scale optimization enhances the system performance. But before I talk about my approach, I want to go through with you what's the conventional approach. The conventional approach usually uses one single electrode to perform this 2 process. They reduce oxygen to form hydrogen peroxide, and then they reduce hydrogen peroxide to form hydroxyl radicals. However, there are some inherent incompatibility between these 2 processes. The hydrogen peroxide production requires a flow-by gas diffusion cell, like I showed you earlier. So in this way, we can provide sufficient mass transport, and the potential for this process is about 0.35 volts. However, the hydrogen peroxide activation process requires a porous electrodes that submerged in underwater. In this, we can use flow-through to enhance the convection and the diffusion of mass transport. And the electrochemical potential for this process is actually 0.8 volts. So as you can see, configuration-wise, for this 2 process, we want to use 2 configuration. And electrochemical-wise, we want to use different potentials for different process. However, none of this can be achieved if we design the electrode in this way, having 2 processes on a single electrode. So what if we just separate them? And then here is the final prototype I developed. As you can see, we have 2 electrochemical systems connecting in series. First, we have the water flows through the air diffusion electrode to generate hydrogen peroxide. After hydrogen peroxide is generated, it goes through the stainless steel for hydroxyl radical production. And here we operate as a flow-by gas diffusion electrode. And here we operate as a flow-through high surface area electrode. And additionally, the potential is optimized separately without applying the same potential. And here, as a result, the Faraday efficiency basically shows the selectivity for the hydrogen peroxide production. And the hydrogen peroxide utilization shows the selectivity for the stainless steel electrode. And as you can see, by simply separating these 2 processes using different configurations and apply different potentials, we achieved a much better performance without any improvements in the material innovation. 2 of these electrodes are all made of very commercially available materials. So here, hopefully I convinced you the electrochemical method is a very selective process that can advance the development of distributed system. So now I want to switch gear a little bit and talk about my postdoc work on membrane separations. Membranes is an amazing technology that can separate the unwanted species like metals or salts from water. However, membranes are often suffered from their inability to remove small and neutral organics. However, these small and neutral organics can easily be oxidized by catalytic process. For example, when we have peroxymonosulfate, PMS, and catalyst, we can easily produce sulfate radical, and the sulfate radical easily oxidize those small and organic contaminants. And for my postdoc work, I focus on combining these 2 technologies into a reactive membrane. So first, I want to introduce some of the perceived benefits of this reactive membrane. What makes them so attractive? What makes me want to study them? The first one is the elevated local concentration. When you think about a membrane, it selectively allows the water to go through the membrane, but rejecting all the solutes. Therefore, usually we have a concentration polarization that has an elevated concentration of the solutes near the membrane surface. And from the reaction kinetic part, we know a higher concentration usually give us a higher reaction rate. So here it's promising to increase the reaction rate by the rejection. And also we know membrane is selective. By tuning the selectivity of a membrane, we can spatial separation the preferred species or the target species versus the interference species. And this could potentially enhance the overall system selectivity for the transformation process. And finally, membrane provides a good platform to confine the catalyst under a nanoscale confined environment. And under confinement, the catalytical performance will be increased significantly. And also under confinement effect, the reaction mechanism may switch to form more useful and more stronger oxidants towards contaminant transformation. But I talk a lot about the perceived benefits. However, I want to mention some existing drawbacks of this study. All of this study usually was conducted from lab scale experiments, and those conclusions or these perceived benefits are concluded from certain experimental conditions, and these conditions may not be generalized. Actually, we see some contradictions between literatures. Additionally, even though sounds amazing, we do not know how we design the membranes. We do not know what's the best membrane properties. We do not know how we operate under what conditions. In order to address this, I started develop numerical modeling approach rather than experimental approach, so we can study these systems more comprehensively. And here I want to show you 3 showcase scenarios how we use the numerical modeling to design the membrane and provide and test the perceived benefits, see if they are actually always the case. The first question I want to ask is how much catalyst is suitable to coat on the membrane? Specifically, I want to discuss this type of membrane with the catalyst coated on the membrane surface. So here from our model simulation, we can see the PMS activation rate, the overall reaction rate, will be a function of the rate constant. For simplicity, you can just imagine the PMS activation rate constants as the amount of catalyst you are coating on the surface of the membrane. As we coat more and more catalyst on the membrane, initially we have a surge in the reaction rate. However, the increase becomes marginal after we hit certain point. That's because we reach a mass transport limited regime. So initially, we are lack of catalyst, the reaction is limited by the catalyst. And later on is the mass balance. So the balancing between the reaction and the mass balance actually can find us a sweet spot, like marked on the gray marker, for the optimal catalyst coating. So here, from the numerical approach, we provide a very straightforward way to determine the optimal catalyst coating. And another very interesting question is why, like I mentioned, so many research contradicts from each other. Again, I want to focus on the membrane with catalyst on the membrane surface. And specifically, I want to further discuss the elevated concentrations. Some people see they have elevated concentration on the membrane surface, but some people observe differently. And the reason why behind that is actually people coat different amount of catalyst on the surface. For example, here, the yellow line is if the concentration profile if you have no catalyst. And when we start to coat more and more catalyst, the concentration in the boundary layer starts to drop. And when we start to coat at the optimal amount or the excess amount, actually the concentration polarization profile is not going upward, but downward. So that's why people observe different trend in their performance. So by comprehensive and systematically evaluating several catalyst coating scenarios, we explain why the contradictory result. And that's because the different coating regime of catalyst. And finally, another question I want to address is we know confined catalyst in a nano environment is great to enhance the catalytical performance and also affect the reaction mechanism. However, I'm also wondering when we confine the catalyst into a very, very small pores, whether the catalyst can enter the pores. So here, this figure shows the PMS, the oxidant utilization efficiency, under different pore, even under different pore size. As you can see, for example, by confining the pore size, we increase the reaction from the slow reaction regime to the fast reaction regime. But if the pore size is very small, there are still no PMS entering the pores, so there won't be any reactions. So that actually contradicts with the existing intuitions that we want to confine the catalyst to a smaller pores because of the activation. And eventually there will be a sweet spot for confining the catalyst under nanoscale environment. We want to something below 1 nanometer, but probably not below 0.7 nanometer. So the PMS can still enter in the pores. So for the sake of time, I do not want to introduce more of the analysis we did, but I want to highlight the implication of this work. So far, there's no design principles to guide the development of the membranes. And by using the modular approach, we propose design principles, and these design principles can be used to start the membrane design by knowing the water composition. We know the composition, we know the treatment performance, we can design what's the proper membrane property, and also how we operate this most effectively. So at the end, I want to go back to my vision of the future environment. Here's how I'm envisioning the future environment using distributed systems. And by develop selective treatments using electrolysis, membrane separation, and the combination of these two technology, I believe there'll be very different combination of distributed systems I can develop. And those will bring our environment to a more sustainable future. So at the end, I want to acknowledge both my PhD advisor and my postdoc advisor, and my two amazing academic families. And at the end, I want to acknowledge the support from the funding agencies and the research facilities. Thank you very much, and I would like to take any questions you may have.
So yeah, people can unmute themselves and ask the question or put it in the chat. The best would be if you raise your hand so we can call on you. So we have a few minutes for questions.
I have a question. Sorry, I can't do anything that you said, Manish. I just shout it out. First, thanks for the very nice talk. I really liked your slides. They looked, very good. I have one comment. I'd encourage you, for all of your experimental data to put the conditions at the bottom of the slide. It just helps a little bit with the interpretation. But my question for you is on slide 12.
Okay.
You were kind of talking about the stainless steel catalyst system and that it doesn't work for negatively charged contaminants. Yes. Many of the contaminants of concern would be negatively charged. They're more mobile. They're more able to kind of get to the treatment plant or the water source in the first place. And so, do you have any thoughts on how you can improve performance for those anionic, more polar contaminants?
Yes, actually here I'm mainly talk about the cathode process, right? So the cathode repels the negatively charged contaminants, but also we've been working on anodes. The anode is positively charged. Actually I didn't highlight much on my system. I only talk about the cathodic part, but also we have anodes in the overall system, and this anode is very effectively to remove the negatively charged contaminants because they are positively charged. And analytically, we can provide an oxidizing environment near the anode. So overall, the system will be work.
So you're also producing the hydroxyl radicals
by oxidizing water, yes.
Okay. Great, thanks.
Thank you.
Yeah, may I ask a question?
Yes.
Can you go to 17 for the slides?
Yes.
Yeah, first, nice talk. May I ask a question? How do you determine this optimal point? Why it's like here? How do you determine this optimal point here?
Because short answer is just we find not exactly a point, but a region for the optimal catalyst coating. And then the point I draw here is actually by fitting this kinetics through mechanics momentum kinetics, and we find where's the half saturation index. But mainly I think I want to mean there's a range for the optimal catalyst coating. and that will be a guidance to do that. Because so far, like, I don't think there's a consensus whether there's an optimal coating or not. The sense I got from literature is just people want to coat as much as possible. But here, the main takeaway is we may not need to coat too much of catalyst on the membrane.
Okay, I see. Thank you.
Thank you.
I think we should move on to the next presentation, but thank you, Yanghua. We should thank him one more time, and then Fuhar, if you want to put up your slides. So while Fuhar is putting up his slides, I would like to introduce him and welcome him to the seminar series. Fuhar got his undergraduate from ITBHU in India, and then he did his PhD at the University of British Columbia with Dr. Majid Mohseni. He's currently a postdoc scholar with Professor Lisa Alvarez-Cohen. So let's welcome him.
Hi, everyone, and wonderful to see you all. So today my talk is going to be on emerging contaminants and basically on analytical gaps, treatment technologies, and what I believe would be the critical areas of improvement. So just to give you a brief agenda of what I'll be talking about. So I'll give a brief background about myself, my past and current projects, especially on my doctoral and postdoctoral research, my vision for future in terms of short and long-term goals, a little bit about our teaching experience, as well as a little bit on technology transfer. That's where I'll conclude. So just to give you an overview, as Dr. Kumar said, I did my undergraduate from the Indian Institute of Technology in BHU, Varanasi. And then I moved to Vancouver at the University of British Columbia, where I did my master's as well as PhD. And then I moved to the University of California, Berkeley, where I'm currently a postdoctoral scholar working in Dr. Lisa Alvarez-Cohen's lab, but also working very closely with Dr. Sedlak's lab, which the previous speaker, Yanghua, was also a part of. So just to give you a brief overview, when I did my doctoral research, it was mostly focused on PFAS. And just for anyone who's not familiarized with what PFAS are, these are a group of emerging contaminants, basically called as per and polyfluoroalkyl substances, where basically all the carbon-hydrogen bonds are replaced by carbon-fluorine bonds. So on the top left side, you can see one common example of a category of PFAS, or perfluoroalkyl substances, called PFCAs, where you have a carboxylic functional group. And on the right side top, you can see a sulfonic functional group. Now, these are the two very common forms of PFAS that are being studied or encountered in the world. They're also categorized by long and short chain. So they're compounds that are either categorized as long chain compound in the both sulfonic as well as carboxylic groups. And at the bottom left, you can see a compound with an 8-carbon carboxylate group called P4. And on the bottom right side, you can see another very commonly detected sulfonic functional group, PFAS, called PFOS. And these are the two very commonly studied PFAS that were out there when I started my PhD. Highly regulated and being studied for toxicity. So these are extremely health problems and are regulated in the nanograms per liter range in the drinking water systems. So my doctoral work was actually on a technology called ion exchange. Now, for anyone who's not familiar with the process of ion exchange, it's basically a polymeric resin that is functionalized by a positive or a negative charge. So here in the image on the left side, you can see a positively charged ion exchange resin with the quaternary ammonium functional group. It's neutralized by chlorides. And when it's put in water, it basically exchanges these chloride ions with dissolved organic matter, which is represented as DOM, or PFAS, which are mostly negatively charged. And the beauty of ion exchange resin, the reason I chose this topic was that these could be recycled and regenerated. So the concept is, if you put it in a high sodium chloride concentration or a high brine concentration, this reaction can be reversed and you can regenerate and recycle the resin back. So I won't go into too much details about PFAS and ion exchange resins, but if anyone is interested, I'll be happy to share my review article that was published on the removal of PFAS by ion exchange resins. Considering the timing, I'll just majorly focus on the major outcomes that came out of this work. So in particular, I was looking at the applicability of ion exchange resins for PFAS removal. this was mostly important because at the time I started working on PFAS, ion exchange resins were not that well studied. In fact, there were a lot of other technologies in the drinking water industry that were being tested for PFAS, but ion exchange was not highly studied. Characteristics, and specifically looking at the charge density, the molecular weight, functional group, and the chain length. In addition to that, if it is useful for handle this treated concentrate, or how are you going to manage this PFAS laden concentrate. And finally, the last part of this doctoral work was to do field scale demonstration of this technology. So just to give you a brief overview or the high level overview of some of the major findings of this study. So here in the figure on the y-axis, you can see percentage removal of different compounds, and x-axis is basically PFAS with dissolved organic carbon of different types. Now, the black bar represents P4, the orange bars represent PFOS, and the blue bars represent TOC. Now, one of the major findings of my doctoral research was on these organic contaminants. Now, I would like you to focus on these two major categories, the fulvic acid and the humic acid. Now, in my studies, I figured out that the humic acid fraction had a very low removal, or if you have water with a humic acid fraction, the removal of PFAS is significantly impacted. And that was one of the major things I was looking into during my doctoral work. So if you look at it from a perspective of an ion exchange resin, it's basically a highly interconnected micropores and microporous channel. And for a PFAS molecule to be removed, it has to be able to penetrate inside these pores to be successfully removed. So what happens is, if you have a water that is just pure deionized water, all these PFAS molecules can actually penetrate inside the resin sites and be removed. But if you have compounds like fulvic acid, which are also negatively charged, they can compete with these PFAS compounds for these sites. So this is one of the major findings that we found, that this can reduce the amount of active sites. But especially if you have bulkier groups like humic acid, they can actually block the pores. And when you block the pores, your removal is significantly impacted because a majority of the sites are not accessible for removal. So this was one of the major findings, or the first stage of my doctoral work. Now, moving on, the next part was actually to look into the regeneration and reuse aspects of these resins. Now, when I was starting this work, the PFAS specific resins were not something in the market. So I was using conventional resins that are typically used for organic matter removal. So we tested a range of different different salts like sodium chloride, bicarbonate with sodium sulfide, as well as combination with caustic. And a range of different concentrations as well as contact types were tested for PFAS removal as well as organic removal. So I'll just go over the high-level results from this study. So here on the y-axis, you can see the concentration of PFAS in the brine, and x-axis is the concentration of sodium chloride increasing from 0 to 20%. So on the figure on the left side, as you can see, increasing the sodium chloride concentration actually plateaus at 10% sodium chloride. So basically, that's the most optimized sodium chloride concentration that would be useful for recovering a lot of these PFAS compounds. Now, if you move to the figure on the right side, again, on the y-axis is the same PFAS concentration in brine, but x-axis is the contact time. And basically, we needed to ensure how much time do we need. And what we observed is that increasing the contact time basically increases the recovery of these PFAS compounds, and it kind of plateaus around 120 minutes. So what was observed from this study is that the recovery of PFAS increases by 10% sodium chloride, and the most optimized contact time is about a 120 minute. And again, the similar study was done for DOC, which was also recovered to the highest extent by this end. But I'll move on to the next part, which was actually once you have these PFAS recovered from these resins, what do you do with these concentrates? So one of the major studies that I did with these concentrates was to actually look at destruction processes like UV sulfide. Now here on the figure on the y-axis, you can see the PFAS concentration in these concentrated brines. X-axis is basically the UV dose, either as time or in joules per centimeter square. And basically, the study indicated that if you use 4 millimolar of sodium sulfide with these UV doses, about 36 hours of contact time or 180 joules per centimeter square dosage is required to basically completely eliminate all these known PFAS concentrations. And again, we did some defluorination studies, and the recovery or basically the defluorination rate was about 50% for these compounds. Ultimately, the next stage or the final stage of my doctoral work was actually to test these or replicate these in a real world scenario. So what we did was we actually did some pilot testing and tested regeneration versus single use capability of the resins in these long-term operations. So here in the figure, where we tested the regeneration and reuse of a single-use versus reusable resin. So on the y-axis here, you can see the concentration of GenX, which was spiked to Middle River surface water, which is basically a river where the pilot plant was installed. Now here we have on the x-axis the bed volumes of water that is being treated. Now for anyone who's not familiar with the concept of bed volume, basically it means how much mLs of water is being treated by 1 milliliter of resin. And that milliliter of the resin can actually also be translated to a dry weight, which is around 250 milligrams per ml. Now, the yellow bars here represent a PFAS-specific resin, which was an A592, which was supplied from basically from Purolite. And there's another resin called A860, which was a regenerable resin, basically used for organic applications. So the A860 was actually regenerated every 15,000 bed volumes, while the A592 was a single-use resin. Now, if you look at the yellow bars, basically around 60,000 bed volumes, the A592 indicates a saturation or basically a breakthrough that the resin cannot remove PFAS anymore. The A860, on the other hand, was indicating the saturation at 15,000 bed volumes, but because it was regenerable, we were able to recover and regenerate and reuse the resin in multiple folds. And one of the major outcomes of the study was to indicate that a regeneration-based approach can prolong the life of the resin in comparison to a single-use resin. Now, this was what I did in my doctoral research. Now, as I transitioned to my postdoctoral work, my shift changed from a drinking water treatment to a hazardous site treatment perspective. So in the drinking water side, I was trained on using ion exchange, adsorption, and UV-based destruction as well as reduction processes. I transitioned to learn or diversify a bit more towards hazardous site removal. And when I started that, I realized that PFAS are more than PFOA and PFOS. It definitely has carboxylates and sulfonates that I mentioned, but it also has a lot of other compounds that are being detected, like sulfonamides. It has compounds like fluorotelomers, which are unsaturated PFAS, having carbon-hydrogen bonds. There are also ether compounds like these GenX and Medona. Now, if you look at the figure on the bottom left, the first pie chart actually indicates the composition of an aqueous film forming foam, or an AFFF that they call. And you can see here a majority of the composition is in the blue pie. And the blue pie here is actually zwitterionic precursors, which a lot of us don't know exactly what these are. And the second pie chart indicates if this AFFF or a firefighting foam is actually applied to a soil, what sticks on the soil. And you can see that these zwitterionic precursors are the ones that stick a lot more on these soils, while the PFSAs or PFCAs that we predominantly were studying were like around 10 or 20% of these compounds. So that's where I started getting interested in looking at these precursors or these unknown compounds and how can we better figure out a way to detect these compounds. So in my postdoctoral work, what I was actually focusing is learning on the total oxidizable precursor assay. And this is something that is used for measuring these unknown compounds. And it was actually discovered in Dr. Sedlak's lab at Berkeley. And it was discovered about 10 years ago. So what happens in a total oxidizable precursor assay is you subject these water sources or these contaminated sources to a lot of oxidants, basically hydroxyl radicals, and it oxidizes all these unknown compounds. For example, here the C8 ECF precursor to a known compound like P4. Similarly, you can oxidize other compounds like fluorotelomere precursors to a group of known compounds. The advantage of this top assay was that it's highly sensitive. It's widely available because it's a very simple technique. You just need a water bath to basically oxidize these compounds, and it also gives you information on the chain length of these compounds. So this is what I tried to learn at Berkeley as a postdoc. And what was the most important part of this work was I was able to translate this work on hazardous site remediation in different aspects. So just to highlight the fact that by working on this top assay right now, I'm leading the EPA's standardized top assay development protocol. So this top assay was discovered about 10 years ago, but still until now, every different group that tries to do a top assay does not have a standard way. So some people use a UV-based oxidation, some people use acidic persulfate oxidation activation, some use a basic persulfate oxidation. There's no standard way of knowing how to know when the oxidation is complete. So I'm actually leading that effort with the EPA by being here at Berkeley to develop a standardized top assay. And this actually involves a lot of coordination with analytical labs as well as industries that make these standard compounds. So making or development of new analytical compounds for PFAS for top assay protocols. But I was also able to explore this analytical skills or analytical training that I got towards fate and transport. So right now I'm actually leading an effort at Berkeley on fate and transport and biotransformation of these PFAS precursors in the environment, especially looking at these unknown compounds. What do they form? How do they stick in the soils? How do they move to the groundwater? And what are the transformation products that they can form over a long period of time? And in addition to that, I've also done some experiments or some work on destruction of PFAS, particularly using in situ chemical oxidation using persulfate for treatment of soils or basically solid matrices. Now, I'll just highlight that, this is just one of the first studies that my work resulted based on my postdoctoral work, which compared all existing analytical techniques that are out there for a single source for measuring PFAS and AFFF. And this is something that was very important for both the scientific community as well as the industrial world out there for knowing which technique is actually right for measuring PFAS in their sources and what could be the areas of improvement that could be utilized for improving the PFAS analytical techniques. And I'll be happy to share this paper with anyone who's interested in learning more about it. So just moving forward, what I would like to highlight is my future vision is combining all this knowledge that I gained from treatment technologies or drinking water treatment with this analytical work and hazardous site treatment for advancing protection of our natural resources and doing sustainable engineering. So I will definitely continue working on emerging contaminants. I'm looking forward to actually diversify to different type of PFAS. In fact, also looking at other emerging contaminants in the field of pharmaceuticals, algal toxins, and even heavy metals. In fact, a lot of work I did on ion exchange involves metals, and this could involve recovery and recycling of rare earth elements too. And I'll discuss that a little bit moving forward. But in addition to that, I'm also open to exploring other avenues and looking at how this knowledge that I've gained could be adopted to different fields like colorimetric sensing of contaminants, resource recovery, water reuse, and air protection, and also reflecting or using this for environmental justice. So just to give you an overview of how this would look like. So in terms of colorimetric sensing, that is something I feel would be very important moving forward and is one of my short-term goal is development or using nanoparticles for contaminant detection, especially colorimetric sensing. So that could be easily done. Right now, all methods that we have for PFAS or any other emerging contaminants require very specific instruments or high-end instrumentation with trained operators. So how can we simplify this detection of emerging contaminants? And that's something I really want to focus on moving forward is how can we actually make the detection of all emerging contaminants simplified that could be done without the use of sophisticated instruments or without the use of trained operators. The next objective of my short-term goal is also resource recovery, especially looking at rare earth metals. Now, the reason I'm into this field is because rare earth elements are used in a lot of electronic industries, and these electronic industries also have a lot of PFAS. So this is something where both of my expertise could be utilized for advancing the science and developing technologies that are both good for the scientific community as well as the industry. In addition to that, I'm also looking or focused on expanding the knowledge or the training that I've gained to advance the destruction or treatment of wastewater biosolids. And this is a very underexplored field in the environmental area, because a majority of contaminated site remediation are focused on AFFF or firefighting foam related defense sites. But wastewater biosolids also contain a large amount of PFAS, and these are being used in agricultural fields. So I want to also diversify into the agricultural and environmental sector on that front. In terms of long-term goals, my vision is actually on developing water reuse techniques, and again using these techniques to develop more sustainable water reuse techniques that can be used for houses, industries, as well as for agricultural water reuse. It could also have implications for air pollution as well as environmental justice. The reason I want to focus a little bit more on environmental justice is because a lot of these contaminants or these pollutants end up getting into marginalized communities or communities that are always at disadvantage. So developing techniques that could help resolve these issues would be one of my focus. In addition to that, I would just also like to highlight that I have also worked a lot with machine learning or integration of artificial intelligence into these environmental matrices. So right now I'm leading the CERDIP, or basically US DoD's forensic studies challenge sample studies. And basically what that means is we are developing or testing all the existing forensic models to do PFAS source apportionment, which means that if you have an unknown sample collected from an environmental site, how could you tell whether it was an airport, wastewater, or a landfill, or any other source? And again, this is critically important because as more and more litigation on PFAS sources get underway, or any other emerging contaminants get underway, sources or tools like these forensic tools are going to be very important. In fact, my vision moving forward is also integrating fluorine NMR with or a hydrogen NMR into these forensic approaches to basically differentiate or better quantify these sources. And again, I would also be very open to, or I'm very curious about using such kind of AI or machine learning tools for the freight and transport models, especially on studies on biosolid application on agricultural soils or any other contaminated site where PFAS are being mobilized to drinking water sources or to our food ecosystems. So just to highlight, I have a very strong track record of having publications. I have, in fact, more than 10 first author publications in top-tier environmental engineering journals. I have also had very successful track record of securing funding. At Berkeley, I'm currently managing 2 of US DoD's projects, basically one for Dr. David Sedlak and one for Dr. Lisa Alvarez-Cohen. The second CERDIP project, basically I was involved from a proposal writing stage, including recruitment, training, and development of the financial plan for the entire grant. I've also experienced securing or applying for USPR as well as NSERC grants in India, basically in Canada as well as in the USA. And in future, I would like to, leverage my training to secure grants from DoD, DOE. The work also aligns pretty closely with the work of USD and NEFA grants, as well as certain EPA RFPs that would be coming in this area. In terms of teaching, I would like to highlight that I have been an instructor for environmental data collection and analysis course at the University of British Columbia when I was doing a Ph.D. And this was basically a course on environmental statistics. In addition to that, I did my Ph.D. in the chemical and biological engineering department, where I was either an instructor or a teaching assistant for a lot of chemical engineering courses like states of matter, heat and mass transfer, chemical kinetics. So with this knowledge, I'm very comfortable teaching courses on environmental chemistry, wastewater treatment, transport processes, or any other departmental needs, including online courses that would be be developed. Now, finally, before I conclude the talk, I would just like to highlight a lot of my work is actually translatable research. So when I started working on PFAS and ion exchange at UBC, it was not known that this technology could be useful for PFAS remediation. But by the time I finished my PhD, my work ensured that the university was highlighted as a premier institute in North America for doing PFAS work. In fact, my work also led to the development of a patent, which was highly captured by field demonstrations and news all over the world. Similarly, at Berkeley, I have been able to showcase the university and the department on a global podium. I'm one of the nominated candidates from across the entire UC-Berkeley campus to represent the group at the Nobel Laureate meeting in chemistry and discuss environmental chemistry at the global level. In addition to that, as I said, I have a strong track record of funding, publication, but also on entrepreneurship. I am a board member for Berkeley's postdoctoral entrepreneurship program, and I basically help and guide a lot of startups in raising funds, as well as getting them the guidance on filing patents and securing funding moving forward. So with that, I just would like to acknowledge my postdoctoral advisors, Dr. Lisa Alves-Cohen, Dr. David Sedlak, my doctoral advisors, Dr. Majid Mohseni and Benwa Barbo, and my committee members, Dr. Anthea Berube and Linden, and also my collaborators with whom I've worked entirely or in very close collaborations with during my postdoc, including Dr. William Mitch at Stanford, Moha at EPA, Dr. Sebastian Save at University of Montreal, and Dr. Chris Higgins at School of Mines. And with that, I'll be happy to take on questions.
All right, we have 4 minutes for questions, so whatever mode you prefer.
I'll chime in again. So nice talk. I really like, just a comment first, I really like what you talked about, working with the EPA to standardize the TOP method, and also your leadership of CERTIP projects. I feel like that would make a strong impression on me, in a real interview, that you're ready to go from day one and, kind of start the job as professor. So nice job there. My question is on the first part of the talk, the regeneration. If I saw correctly, there is no solvents in your regenerants. In our experience working with different ion exchange materials, resins, modified resins, ion exchange membranes, some solvent is usually needed to pull off, especially the long chain species. Our hypothesis is just kind of like a dual absorption mechanism, kind of the electrostatics of the ion exchange reaction and some hydrophobic interactions with the base polymer. Can you speak a little bit like why solvents not required, and maybe the conventional ion exchange materials are better than the newer ones if you don't need solvent to regenerate?
Yeah, no, thanks, Lee. That's a wonderful question. And actually, yeah, so this, again, as I said, I started working on PFAS about a decade ago. And at that time, PFAS-specific resins were not something in the market. They started developing in parallel to what I was doing. So I could see in my final stage of the work, where we were actually doing field testing, that's when A592, which again is not like widely used as a PFAS-specific resin, but that was the first one that was being introduced by Purolite as a PFAS-specific resin. So my work was actually on Purolite 860. And this is traditionally an organic scavenger resin that's just basically used for removing humics and other organic matter from water. And it's really good for regeneration because the functional group is not what a PFAS-specific resin has. The downside of that is, of course, its kinetics are very, very slow. So if you imagine an ion exchange resin that's used for PFAS removal, the empty bed contact time would be around 2 to 3 minutes. This resin actually needs about 60 to about 2 hours for removing. So at that time, when the knowledge was not there on what could be used, I basically was testing that resin. From a practical perspective, maybe it's not ideal for removing PFAS because it would definitely need a lot of contact time, but that's again indicative of that the bond is much weaker. It's not the way a PFAS-specific resin binds and requires an organic solvent. So that's why a salt-based regeneration was a bit more effective in this scenario.
Thank you.
But with all the PFAS specific resins I've had the experience, it definitely needs its organic solvent like methanol or ethanol, or some combination of salt and organic solvent.
Yeah, thanks. Nice work.
Maybe we can take one more question. I can ask the question. I've been thinking about this too. So, how would you integrate machine learning in what you want to do, and what specific part of your work would you use it for?
That's a wonderful question to talk about. So, I mean, machine learning could definitely be integrated, as I said, in the forensic models. So, I have had the experience of using or developing a forensic model based on the top assay data, and we have used it to basically separate out fingerprints of landfill, wastewaters, and AFFF. But as I said, integration of that with additional fluorine NMR based approaches could be even more beneficial because fluorine NMR, just like the top assay, does not need a very sophisticated instrument. There are again a lot of machine learning models that are coming out of suspect screening, which are very precise. But again, it's very limited to labs that have trained operators and these high-end instruments. So my idea is to simplify this on that end. It could also be used for freight and transport modeling. So especially when you have a contaminated zone with either biosolids or implication or application of AFFF or any other contaminant. What could come out into your groundwater or how this transformation could work out, or even integrate data to see what processes could be basically used to immobilize this movement of these contaminants to your drinking water sources. Yeah, and again, I'm curious to collaborate and discuss even further with again the departmental expertise on these topics to further enhance this knowledge.
All right, I think we could formally close the seminar, but people hang out and talk. I unfortunately have to go, but great job, both of you.